Hello and welcome to Unit 2.2. During this video, we'll discover different types of polishing treatment technologies for water reuse, including constructed wetlands, membrane filtration, and UV disinfection. At the end of this module, learners will be able to identify different types of constructed wetlands and their features and functions, understand and explain the main types of membrane filtration used in wastewater treatment for reuse applications, and describe the disinfection process from ultraviolet radiation and compare it to other disinfection options. The design of wastewater treatment for reuse is about matching supply and demand. It's by comparing the quality of water demanded with the quality of water available that treatment systems can be designed. Depending on the end use, water can be reclaimed following different levels of treatment. Membrane filtration and UV disinfection treatment steps are usually part of tertiary or advanced treatment. Constructed wetlands can be used to provide some secondary treatment. However, they may also be used following secondary treatment in a polishing capacity. Constructed wetlands are engineered systems designed to mimic the natural processes of wetlands for the treatment of wastewater. They use a combination of physical, chemical, and biological mechanisms to remove pollutants, relying on the interaction between water, vegetation, filter media, and microorganisms. These systems are particularly valued for their low energy requirements, simplicity of operation, and capacity to deliver robust treatment performance under variable flow conditions. Two broad categories of constructed wetlands can be distinguished. The first includes vegetated wetlands with filter media, where the treatment relies on the combined action of plants, microorganisms, and filtration through a porous substrate such as gravel or sand. The second category comprises surface flow wetlands, which operate more like shallow ponds or basins, where sedimentation and plant uptake dominate the treatment processes. In these systems, water flows above the soil surface and suspended solids settle, while emergent vegetation promotes nutrient removal and provides oxygen transfer to the rhizosphere. Depending on the retention time of water in the wetland and the location and season, there can also be a not insignificant level of UV solar irradiation, which contributes to disinfection of microbes. Within subsurface flow systems, those using filter media, two principal configurations are used: vertical flow and horizontal flow wetlands. In vertical flow wetlands, wastewater is intermittently loaded onto the surface and percolates vertically through the substrate, enhancing oxygen transfer and promoting nitrification. These systems achieve efficient organic matter and ammonia removal with limited space requirements. Horizontal flow wetlands, by contrast, convey wastewater horizontally through a planted gravel bed below the surface. They are well suited for denitrification and provide steady, passive treatment with high retention of suspended solids. By combining different types, such as hybrid systems that integrate vertical and horizontal stages, constructed wetlands can achieve advanced treatment levels suitable for diverse applications, including domestic, agricultural, and industrial wastewater. Their ecological design, low operating costs, and landscape integration makes them an increasingly attractive option for sustainable wastewater management. Filtration and membrane technologies are advanced physical separation processes widely applied in wastewater treatment to remove suspended solids, microorganisms, dissolved substances, and other contaminants. These systems operate by forcing water through semi-permeable membranes that act as selective barriers, with separation efficiency determined by the membrane's pore size. Microfiltration membranes have the largest pores, typically ranging from 0.1 to 1 micrometer. They effectively remove suspended solids, algae, and most bacteria, but allow dissolved organic compounds, nutrients, and salts to pass. Microfiltration is primarily a physical treatment process, providing excellent clarification and pathogen reduction when combined with disinfection. Ultrafiltration features smaller pores between 0.01 and zero point 0.1 micrometers. It retains colloids, fine suspended particles, and viruses while allowing most dissolved ions and small organic molecules to pass. Ultrafiltration achieves both physical and partial biological purification, producing high-quality effluent suitable as feedwater for advanced treatments such as reverse osmosis. Nanofiltration bridges the gap between ultrafiltration and reverse osmosis, with pore sizes of approximately 1 to 10 nanometers. It can remove divalent ions such as calcium and magnesium, color, and low molecular weight organic compounds. Nanofiltration offers chemical-level treatment performance, effectively softening water and reducing dissolved organic carbon and micropollutants. Reverse osmosis uses the densest membranes with pores less than 1 nanometer, allowing only water molecules to pass. Under high pressure, reverse osmosis removes nearly all dissolved salts, metals, organic compounds, and pathogens. It provides complete physical, chemical, and biological purification, producing high-purity water suitable for reuse or discharge into sensitive environments. In membrane filtration systems used for water and wastewater treatment, spiral wound and tubular configurations are two common types of filter modules. They differ mainly in structure, operating conditions, and suitability for different feedwater qualities. Tubular filter membranes are formed as a tube, typically 5 to 25 millimeters in diameter, and the feed flows inside the tube. The permeate passes through the membrane wall, while the concentrate continues along the tube and exits at the end. They are used mainly for microfiltration and ultrafiltration of highly polluted or viscous fluids, such as industrial wastewater, sludge streams, and bioreactors. Spiral wound filters consist of flat sheet membranes wrapped around a central permeate collection tube in a spiral pattern. Spacers are placed between layers to create channels for feedwater and permeate flow. They're commonly used in nanofiltration and reverse osmosis systems for relatively clean feedwater. For example, drinking water treatment or tertiary wastewater polishing. Ultraviolet disinfection is a physical disinfection process widely applied in wastewater treatment, particularly in tertiary treatment and wastewater reuse applications, to inactivate pathogenic microorganisms without the use of chemical disinfectants. UV disinfection works by exposing wastewater effluent to ultraviolet radiation, typically at wavelengths of around 254 nanometers, which corresponds to the germicidal region of the electromagnetic spectrum. The radiation penetrates microbial cells and damages their nucleic acids, DNA and RNA, preventing replication and rendering the organisms non-infectious. For effective disinfection, UV performance depends on the UV dose, which is determined by the intensity of the radiation, the exposure time, and the water quality parameters, including turbidity, suspended solids, and UV transmittance. The advantages of UV disinfection include that there's no addition of disinfectants or residual chemicals, making it ideal for water reuse where chemical byproducts are undesirable. There's also no formation of harmful disinfection byproducts, unlike chlorination or ozonation. UV provides rapid inactivation against a broad range of microorganisms, including bacteria, viruses, and protozoa like Giardia and Cryptosporidium, which are resistant to chlorine. It also has a compact footprint, making it suitable for modular installation and retrofitting in tertiary treatment systems. Some limitations of UV disinfection include that there is no residual disinfectant effect in the water following treatment. Unlike chlorine, UV provides no residual protection in distribution or storage systems, so post-disinfection contamination is a risk. It's common to see chlorination added following UV treatment to account for this. UV treatment is sensitive to water quality. Suspended solids and high turbidity can shield microorganisms from UV light, therefore reducing effectiveness. Therefore, the water must be treated sufficiently prior to UV treatment. Maintenance can be significant. Lamp sleeves require periodic cleaning, and lamps have a limited life, typically around 8,000 to 12,000 hours. The continuous power supply needed for the lamps also means that energy consumption can be significant in large facilities. UV disinfection is a robust, non-chemical and environmentally friendly technology well suited for wastewater reuse, where maintaining high-quality effluent and minimizing byproducts are priorities. However, it requires well-clarified effluent, careful maintenance, and may need to be combined with a residual disinfectant such as chlorine or peracetic acid when post-treatment microbial regrowth is a concern. And finally, here are 3 important takeaways from this unit. Constructed wetlands need space, and the treatment efficiency can be variable, but they use gravity and natural processes, limiting operational and maintenance costs. Membrane filtration can be effectively adapted for many uses, but requires pre-treated water. The filter units need regular maintenance and eventually replacement, and energy costs can be significant. And finally, UV disinfection doesn't leave toxic disinfection byproducts, and it's effective against all microbes, but it requires clean, clear water to penetrate, the energy cost can be high, and there's no disinfection residual. Thanks for your attention, and don't hesitate if you have any questions.